Hello, everyone. Good morning, good afternoon, good evening, depends on where you are. Welcome to one more Telecom seminar, which is hosted by Technology Innovation Institute in Abu Dhabi. I'm Dr. Daniel da Costa, currently a principal researcher at TII. For today, it's a great honor and privilege for us to have Professor Vincent as the speaker of our Telecom seminar. In this talk today, Professor Vincent will basically present an overview and new results on distributed learning at the edge of the wireless networks, and with machine learning algorithms interact with the physical limitations of the wireless medium. Before moving to the talk, let me say some few words of Professor Vincent. Actually, he needs no introduction. He is a very renowned researcher, professor of our community. And this morning, after checking his CV, I got very impressed with the number of awards, achievements. The CV has around 170 pages. But let me say some few words. Professor Vincent is currently Michael Henry Strader University Professor at Princeton University. He received many awards and recognitions and honors along his brilliant career. For example, he is a fellow member of many societies, especially at AAA. He is fellow since 1987, if I'm not wrong. He got honorary degrees and professorship in many different institutions. He got many technical contributions and recognitions. For example, the Hall of Fame Award in AAA Vehicle Technology Society, Alexander Graham Bell Medal in 2017. He was recognized many times for education contributions, teaching, mentoring. For paper awards, he got many paper awards in journals and conference, flagship conference like ICC, Globecom, and so on. And basically, if I enumerate all his achievements, I would spend the whole day here. So Professor Vincent again, thank you so much for accepting our invitation. And without further ado, the floor is yours.
Thank you, Daniel. Very happy to have this opportunity to speak today. Good evening, everyone, or good morning, depending on wherever you are. Probably most of you, it's good afternoon. So, I think everyone here knows that machine learning and wireless communications are two of the most rapidly advancing technologies of our time. And of course, neither one of these is a new technology. I mean, machine learning goes back at least to the 1950s. And of course, wireless communications is more than a century old, going back to Marconi and so forth. And even the modern wireless era goes back to the 1980s. So these are not new technologies, but they still continue to advance very dramatically. And one of the things that has happened in recent years is a confluence of machine learning and wireless communications. So I'm going to talk about today about part of that confluence, and we'll see how that goes. So first of all, there are really two aspects to the connection between machine learning and wireless networks. One is using machine learning to optimize networks. And of course, that's a very natural application of machine learning because, wireless, any communication network has a lot of problems, solves a lot of problems that can be solved using machine learning, like decision problems, like decoding, estimation problems, like channel estimation, control problems, like routing. These are all the kinds of things that machine learning is quite good at. And so it's very natural to apply machine learning to these kind of things, particularly in the modern era when we don't have as good of models as we once had due to moving to new parts of the spectrum and increased interference environments and so forth. Now, so that's a very active area, of course, but I'm not going to talk about that today. What I'm going to talk about today is using mobile platforms, mobile networks as platforms for machine learning. That is learning over networks. So this is a very active area of research today. This one probably doesn't go back so far as some of the other things. And so I'm going to talk about two particular things today. I'm going to talk about federated learning and also decentralized learning. And I'm not going to talk about these in general. That is, I'm not going to give a survey of either one of these, but I'm just going to set up a little bit about what they're about, and then give a few results just to illustrate some of the things that are going on in these areas. So I'll start out with a little bit of motivation, and then when I'm done talking about these two things, I'll wrap up with some conclusions, and I'll talk about some open research issues related to, but mainly to federated learning. Okay, so by way of motivation, let me just say a little bit about state of the art in machine learning. And this is greatly oversimplified, but it just sets the stage a little bit for what I'm going to talk about throughout this talk. So what, as I mentioned, machine learning is not new. It goes back decades, many decades. And there have been other times when it's been prominent. For example, in the 90s, neural networks were all the rage. So why now? We're still using neural networks. Of course, there are new examples and so forth, but why is it all of a sudden such a big deal? Well, one is that more data is available. So today we have tremendous amounts of data, and wireless networks are part of that. That is, gaining data from wireless devices is part of why we have so much data. But also there's data coming from the internet and other electronic means. Also, computing power today is so much more powerful than it was even in the 1990s. So that means that we have, okay, I was just checking the chat. That means we have a lot more computing power, a lot more data, so machine learning can take on a more prominent role. So if I have to, again, oversimplifying a little bit, if I had to say there's a standard kind of machine learning today, it's implemented in a centralized manner, that is, at a data center or on the cloud, in the cloud. And machine learning algorithms have full access to the data. That is, they can touch any of the data they want to at any time. And of course, this model gives rise to state-of-the-art models that have been developed to use this big data, such as deep neural networks. And this can be managed and operated straightforwardly because Google, for example, has provided software to do that. So we have standard tools like TensorFlow, and you can accelerate the performance of those kind of algorithms using specialized hardware like GPUs and so forth. So this is, as I would say, just a very broad view of the state of the art in machine learning today. Now, that kind of centralized machine learning may not be suitable for a number of applications. For example, self-driving cars, that is autonomous driving, first responder networks like emergency response, and healthcare networks like telesurgery and so forth. So these are applications where the certain circumstances may dictate moving learning closer to the edge. So some of the reasons why, first of all, data is born at the edge in many cases. So it's born on our smartphones or IoT devices. So it's already at the edge. And in a wireless network, of course, we have limited capacity uplinks. So that means that if we want to touch this data in the cloud, then it all has to be uploaded through limited capacity links. Also, one of the common things about these examples I mentioned is low latency and high reliability. And you heard about that in a previous seminar by Professor Popovsky. So, you know, and for example, autonomous driving, we don't have time to wait for data to upload to the cloud and to have processing coming on there and then having models or whatever to download back to the edge. So low latency dictates moving some of the computing to the edge. And then another is data privacy. If we, you know, a lot of the data that we collect on our smartphones, for example, is private data, location data, and so forth. We don't want to share that with the world. And the further back we upload it into the network, the more danger there is of that data being compromised. And then finally, a lot of applications really only matters is what's happening locally. Like with autonomous driving, we don't care what's happening, you know, 1,000 miles away. We only care what's happening locally. So, you know, we really can operate locally without worrying about what's happening in other regions and so forth. So we can do machine learning effectively in a small location. So all of these considerations motivate moving learning closer to the network edge, which is what I'm going to talk about today. So I'm just mentioned three network machine learning models. One is standard machine learning, which I already described. So the end user devices collect data, upload it to the cloud, and then that data is processed, models are learned, what have you, optimum decisions are determined, and then that's downloaded back to the edge or to the end users. Another model is federated learning, where data is collected in end user devices, and those end user devices locally try to learn a common model. And then as they each learn their own version of this model, they upload those to a cloud or an edge device like an access point, where those models are aggregated and then returned to the end user devices where they might be updated or even just used directly in that way. Okay, so that's federated learning. I'm going to talk more about that in some depth. And then there's decentralized machine learning, where again, the end user devices collect data, learning takes place on the end user devices, but there's no aggregator. That is, the communication can take place in a peer-to-peer fashion, but there's no one agent who's doing aggregation of the models. Okay, so I'll talk briefly about that at the end. So let me now then talk about federated learning, and so just dive a little bit deeper into that. So, you know, the basic idea here is to enable end user devices to do machine learning without centralizing data. And so some key features of this are, first of all, the data sets are retained on end user devices. Secondly, training is done also on end user devices, and they're training, all the end user devices in this network are training on a shared model. So they're all trying to train the same model. They're just doing so independently with their own local data. And then federated computation. So then once the end user devices have attained whatever local model they've learned, they're going to upload that to an edge node like an access point or a base station. And then that will aggregate the models from the end user devices into a shared model and download that back to the end user devices, where we may iterate again until we get to convergence. So that's the idea of federated learning. Now, federated learning actually is not just necessarily a wireless application. Federated learning originally was developed by Google as just a generic type of distributed machine learning. But if we implement it over a wireless network, of course, the communication to the access point, that is the aggregator, has to go through wireless channels. So that means now we have to worry about the interaction between the wireless channels and the machine learning algorithm. So two things to worry about. First of all, since the wireless medium, of course, is shared, it's a broadcast medium, and it's resource constrained. We have a finite amount of channel resources. So that means because of the resource constraint, only a limited number of devices, end user devices, can be selected in any update round to provide their updates, okay? And secondly, because they have to provide those updates over a wireless channel, transmissions aren't reliable due to interference and other impairments, okay? So this brings up a couple of questions. First of all, how should we schedule devices to update the trained weights on a given update round? And secondly, how does interference affect the training? So we're going to address those two questions. So first of all, scheduling of updates. So we can think about some standard scheduling mechanisms. First of all, the model we have is going to have is we have K end user devices, UEs, user equipment, and there are going to be N channels available to the aggregator or the access point through which these end user devices can upload their models. And N is less than K, otherwise there's nothing to worry about. So this could be an Internet of Things sensor network with hundreds of devices, or it could be a lot of people in an area with their cell phones, hundreds of them again, and we just don't have hundreds of channels to allow them all to upload at the same time. So N is less than K. So one way that the access point or the aggregator, if you will, could schedule is just to randomly choose on each update round, at random, choose N out of K end user devices to upload. So that's random scheduling. Another scheduling mechanism would be to group the end user devices into K over N groups. Okay, so K is the number of end user devices, N is the number of channel resources we have. And then just to go, as we go through iterations of the machine learning updates, we just go through sequentially selecting each group. And then finally, another standard mechanism is proportional fair scheduling, where the aggregator selects N out of K end user devices that have the strongest received signal to noise ratios at the access point. Okay, so random, round robin, and proportional fair, three different types of scheduling mechanisms. And we'd like to compare these in the context of how they work for updating aggregations in federated learning. Okay, so how can we do that? Well, to compare them, we need a performance metric. And here's one that we can use that's very useful. So first of all, just to point out the obvious that for a given end user device's update to be successfully received at the aggregator, first of all, it has to be selected by the scheduler. So the first necessary condition is that it has to be scheduled by the aggregator in order to upload on that round. And secondly, even if it's selected, there's a chance that its packet sending it up its model may not get through. So in addition to being selected, it also, the received signal interference plus noise ratio at the access point has to exceed some decoding threshold. So if the decoding threshold is very low, that means it's a good link and it's likely to be received. If the decoding threshold is high, that means it's a poor link or a poor code, if you will, and the possibility of getting through is low. So based on this parameter theta, so that's one of the first parameter we're going to use here. We can describe a metric to quantify the effectiveness of training, that is to compare different schedulers. And that's the number of communication rounds it takes to reach an epsilon accurate solution. Okay, so now let me describe what epsilon accuracy means. Here, we're going to focus exclusively on problems of minimizing a strongly convex function. So in that case, we know that the primal and dual algorithms reach the same solution at optimality. And an epsilon accurate solution is one in which the gap between primal and dual solutions is less than or equal to epsilon. So that's another parameter of this model is epsilon. So we have theta, the SNINR threshold, epsilon, the accuracy that we're going to try to achieve. And given these, this model and set in some other things, which I'm not going to get into detail here, we can actually come up with lower bounds on the number of communication rounds it takes to converge for these three scheduling algorithms, random scheduling, round robin, and proportional fair. And don't worry too much about the specific form of these bounds. I'm going to give some graphs in a minute, but I'll just point out the parameters that appear here. One is epsilon, which is the duality gap. I already mentioned that before. Another is theta, which is the SINR threshold. There are three more parameters. Alpha, the path loss exponent. So this is a wireless channel, so it has path loss. Beta, which is a measure of precision of learning at the end user devices. So we're just abstract the learning process at the end user devices to this number beta. And then N is the total number of exemplars. And given that, we can compute these lower bounds. G is the number of groups. Remember, we defined that earlier. And then nu is just an integral function that depends only on theta and alpha. So I'm not going to give you the details. I'll give a paper later that has that. So let's take a look for the two cases of high SINR, which is, like I said, a poor code, that is one that's hard to decode, and a good case of low SNR, which less INR, which means it's easy to decode. And on the left, we can see in the case where we have a poor code, we can see that here proportional fair outperforms the other two types of schedulers. And that's intuitively pleasing because when we have a difficulty decoding, we want to have as much signal to noise ratio as possible at the receiver, at the access point. And so we want to use we choose those uploads, those devices to upload, which provide the highest signal to noise ratio at the access point. Now on the right, when we have a low SINR threshold, we can see that round robin outperforms the other two. And again, this is pleasing as well because we can see that if you think about it, the idea of round robin is we give each piece of data the same opportunity to enter into the model. So by going through round robin, we're getting as much diversity in data as possible. And here that outweighs the vagaries of the wireless channel, unlike the case on the left, where the wireless channel takes more of a precedent. And so we have to worry more about signal to noise ratio and things like that. So these are results. These are just lower bounds, but they give us some intuition about how these schedulers work. And we can also look at a specific machine learning algorithm to verify this. So this is a case of training a support vector machine on the MNIST data set. So MNIST data is the handwritten character recognition data. We use 10,000 exemplars here distributed on 100 devices. We're choosing 20 out of those 100 devices for each aggregation. And here we're looking at performance versus the number of communication rounds. And here I'm just going to compare round robin with random scheduling. This is a case of low SINR threshold. And we know that proportional fair and random, at least in terms of the lower bound, are roughly the same. And you can see here that, and on the left we have loss, and on the right we have accuracy. And you can see that they both of these schedulers achieve the same performance if you wait long enough, but clearly round robin is getting there faster. And that sort of bears out what we saw in the previous slide, that for this low SINR case, round robin is the best thing, okay? So one of the conclusions, of course, is that scheduling matters. We can't just choose an arbitrary scheduler, expect it to perform well. So one question we might ask is whether we can optimize scheduling. And an answer to that is yes, we can do that. And how can we do that? Well, one thing is to introduce a design metric to the problem. So an interesting metric, or a useful metric here, is age of information. So age of information, you may know, is a design metric that's entered into communication system design lately, mostly driven by Internet of Things type sensing applications, where the end user devices are energy constrained. They can't necessarily report measurements in real time. So they have to decide when to report. And that means that the measurements, that the information arriving at a central point may not be as fresh as it could be. So in addition to looking at the more traditional measure of distortion to optimize a communication system, we also add the notion of freshness to the data. So age of information gives us a metric to measure freshness of data. So just to think about it, if you're interested in the temperature outside, you really care a lot more about the temperature right now, even if it's not that accurate, than you do about the temperature 24 hours ago, even if you could get that to 20 decimal places. So age of information is important mainly for sensing applications and related things like that, where timeliness is important. So here we can use age of information as a metric for timeliness of updates in federated learning. So for a given end user device I, the age of its information is going to drop to 0 on a given communication round if it's selected to update then. Otherwise, its age is going to increment by 1. So if you let SI of t be an indicator for whether the ith device is selected on the tth round, so it's 1 if the device is selected and 0 if not, then we have this little recursion that keeps the track of the age of a given device. Now we can design a scheduler that minimizes the average age subject to some constraints. And I'm not going to put the algorithm up here, but it turns out it's polynomial. So it can be handled in real time, or at least between updates. It's faster than machine learning, so it can be done while the learners are learning. So if we do that, we get an algorithm called wireless round robin. And then here's an example to compare wireless round robin with another algorithm called maximum pack, which is kind of an optimal algorithm that tries to put get as many devices updating at a given time as possible. And again, we're training a support vector machine on MNIST data, same problem as before. And we have loss and accuracy here. And you can see that wireless round robin outperforms maximum pack pretty convincingly here. And even after 100 rounds, they don't converge to the same point. So clearly we can optimize this is one way to optimize updating of federated learning, the scheduling, by using the average age. Okay, there may be other criteria that give even better performance, but certainly this is doing quite well. Now, another thing to think about with federated learning is privacy. And I want to talk about that just briefly. Hold on, I'm trying to look at the chat at the same time, so let me get rid of that if I can. Okay, sorry, I was looking at the chat. Sorry. An early claim for federated learning was that it was privacy preserving because the data remains on the end user devices. And even I claimed that in some of my early papers, and that's Google claimed that in the beginning. But pretty soon it was shown that that's not the case, that end user data can be inferred from the updates provided by the end user devices to the access point. And in fact, intuitively, this makes sense because, you know, the models are derived from the data, so they definitely depend on the data. So there is some mutual information between the model and the data. And so if there is, you can make inferences about the data. And there's some pretty convincing examples where the data is images, and you can look from the model, you can reconstruct a pretty good facsimile of the images that was used. So privacy of end user data is a concern with federated learning. It's not privacy preserving, but it is privacy enhancing because the data is not forwarded all the way through the network, but it's still not privacy preserving. So how can we deal with this problem? And well, one approach is to use differential privacy to protect end user data. There are other ways, but this is a good one. So what is differential privacy? I mean, most of you probably know, but just in case you don't, let me say a little bit about it. So differential privacy refers to a definition of privacy in which you if you take two data sets which differ only by a piece of private information, okay, then that you're interested in preserving, then that we say that it's different, that data set is differentially private if you can't distinguish between the two data sets by a statistical query with high probability. So you can't query the database and determine this private information with high probability, okay? So there's a mathematical definition, but that's roughly what it means. But you know, there are a lot of definitions of privacy, but differential privacy is useful because it can be achieved quite simply by adding noise to data. So, you know, it's easy to achieve differential privacy. And this approach then can be used in federated learning. But on the other hand, if you add noise to data, I mean, here the data or the models that you're going to be sharing with the access point, that's going to degrade the performance of machine learning. So there's a trade-off between privacy and performance here. And just to see what that looks like, here's an example. This again is using the MNIST data. Here we're learning a convolutional neural network, but it's a similar thing. And what's shown here is testing accuracy versus aggregation time, that's the number of rounds, parameterized by this parameter epsilon. And epsilon is a parameter that appears in the probability bound of differential privacy. And the smaller epsilon gets, the more private the data becomes. So you can see that with no privacy, we get a certain accuracy, which is quite good. As we start imposing greater and greater privacy constraints, we get worse and worse accuracy. Okay, so this illustrates just by a simple example that there is a trade-off between privacy and performance. But nevertheless, privacy is important, and so we certainly should pay close attention to that. All right, well, I want to now, I have about, looks like I have about 15 more minutes, so I want to just shift gears and talk a little bit about decentralized learning. So far we've had this federated learning model where we have an aggregator. In decentralized learning, all the communication is just peer-to-peer. There's no aggregator. Any aggregation, if it goes on, has to go on by communicating with peers and looking at some kind of consensus with your peers, okay? And what I'm going to talk about here is actually some fairly older results that illuminate this problem to a certain extent. But there's a lot of work going in this area now, and this is not intended to be a survey or anything. It's just some some thoughts on this area. So in order to think about distributed learning in general and decentralized learning in particular, we can look at a fairly general model. And that model looks like this. So of course, what we're doing when we learn, we have certainly from learning with a teacher or supervised learning, we have training examples, which are, so usually we're trying to learn a function, right, which maps some inputs X to some outputs Y. And we have a lot of training examples that are already values of inputs and optimal values of outputs Y. And we have N of those, say, and the training, basically the idea of machine learning is to try to learn the relationship that maps X to Y. So that's the sort of very simplified view of things, but that's typically what we have, okay? So we can think about a situation where we have N such training examples. So that's our training database. And then we have M learning agents, okay? So these could be smart sensors, this could be the aggregator, this could be the machine learning, this could be the smartphones in a network or what have you, but they're M learning agents. And then between the learning agents and the training examples, we build a bipartite graph like shown here. And an edge in this graph means that a learning agent at one end of the edge has access to a training datum at the other end of the edge. So in this case, for example, learning agent M has access to training data 1, 5, and N, okay, and so forth, okay? So this is a general model for distributed learning. One special case is centralized learning, where M is 1. So we have one learning agent, and it's connected to everything in the training database. And then we also could do federated learning, could be in this model, but also purely decentralized learning can be in this model, where M equals N. That is, we have each learning agent has its own training datum, and then there may be connectivity based on some physical characteristics like a radio range or something like that. I'll give an example later. But basically, we have this bipartite graph. It describes learning, distributed learning in a fairly general setting. So one way we might do learning in a graph like this, or in a setting like this, is to let each local learning agent, each learning agent learn locally from its data. So like learning agent 1 has 3 data points here, and it could do model fitting based on those 3 data points. And then likewise, the other agents can do learning based on whatever data they're connected to. Now, a problem with local learning, even though it's very natural, is that it's typically incoherent. That is, if you, for example, so each of these agents is going to learn its own model. Its model is a function mapping X's to Y's. And so, for example, if you look at F1 and L1 and LM, they each are going to learn their model, F1 hat and FM hat, for the same, it's supposed to be the same function F. And they both are using the first data point there. But there's no reason why, but they're learning in general from different data. They share one data point, but they only share one data point. So they're not going to learn the same value of the function F. And that means that typically, when they apply their function to X1, they're going to get different values. Okay, so that's called incoherence. And you can show in such problems that incoherence leads to suboptimality. Okay, so the nice thing about local learning is it's local. It respects the local connectivity, but the bad thing about it is it doesn't give you necessarily satisfactory results. So what can we do about that? Well, again, this is an old idea. It comes from 2009 paper here. But what we can do is implement the following kind of algorithm. So we can start out with learning agent 1 and let learning agent 1 learn its value of the function, F. And then before moving on to the next learning agent, learning agent one overwrites the database, the Ys, the targets in the database, with its own estimates of what those Ys should have been. Okay, so that's, it's putting its something about what it's learned from its data down in the database. And then we move on to learning agent two, and learning agent two does the same thing. And you see here they share in this particular case one training example, the second one. So something about what learning agent one learned is going to be part of learning agent two's process. And then once it learns its value of the function, it's going to overwrite the targets and the data that it has access to. And we move on to learning agent three and so forth. And then we just keep iterating through this until we converge. And it turns out that this type of iterative algorithm, collaborative learning, converges to a coherent relaxation of the global solution. So this is a way that we can preserve still the advantage of the local communication topology while achieving the best we can do given the constraints of this graph. Okay, you can prove that by alternating projections, so it's not really that hard to prove. So here's an example. Here we will just assume that we have sensors, 50 of them, distributed at random between -1 and 1 along a line. And the eye sensor is located at point xi, and it's going to observe some function of its location plus noise. And we'll just assume for simplicity that the noise is IID Gaussian. And the regression function f is linear, and what we want to do is learn f. That's the purpose of the machine learning algorithm. And then we're going to build the graph, actually the communication topology, by saying that I and j are neighbors, that is, they're connected in this graph by an edge if they're within r units of each other physically. Okay, so r is a parameter. And then the sensors are going to do kernel learning, and they're going to apply a linear kernel. So this is an easy problem. They've got a linear regression function and linear kernel, but I just want to illustrate the principle here. So on the right, this shows the performance versus connectivity. So on the vertical axis is mean squared error, and on the horizontal axis is R. So the bigger R is, the bigger the neighborhoods and the more connections there are, right? So if R is big enough, everything is connected. And you can see how things work here. So the solid line, which is very close to 0 down there, is the performance here of centralized learning. And as you would expect, it's very, very good because we're doing linear regression, linear kernel and linear regression. On the other hand, the dotted line, the top one there, is the performance of local learning. And there you see it's quite poor until R gets to be pretty large, 0.6. And then it gets to be close to centralized learning. But at that point, there's a lot of connectivity in this graph. And then the dot dash one down there, closer to the, between these two lines, is this, it's called SN train here. This is that collaborative learning algorithm. And you can see that with R only equal 0.2, that much connectivity is enough for this collaborative algorithm to give us centralized performance. Okay, so this is a simple example, but it illustrates what's going on here. All right, I have just a few more minutes, so I'm going to talk about briefly about reinforcement learning. We've been talking about more traditional machine learning up to this point, and then I'll wrap up with some open questions. So, of course, reinforcement learning is a type of learning that adaptively finds optimal strategies without a model. Okay, it's for Markov decision processes where you don't know the properties of the underlying Markov process and so forth. And a type of reinforcement learning that's widely used is Q learning, where Q is the Q function is the payoff function, and you try to learn that iteratively, try to converge to an optimum. And in centralized Q learning, you basically are doing gradient updates on Q. Now, in a distributed setting, we can't compute global gradients, but it turns out that we can combine a local gradient update if we have a distributed setting that is local with we have some connectivity with our neighbors, and we can use their data and our data to form a local gradient. So we can do a local gradient update, and then we can also look to do consensus among neighbors as well. So we combine classic gradient descent, if you will, with a consensus type algorithm on each iteration. And by doing that, even though we don't have we're not looking at all the data together, that is, we're not performing globally optimal Q learning, this kind of algorithm converges to global values as long as we have some connectivity conditions and the tuning parameters of the iterative algorithm behave in a certain way. Okay, so I'm not going to get into the details, but just to point out that by adding, if we have centralized, we want to use gradient descent. In distributed setting, we can't compute global gradients. We can only compute local gradients, which will not converge to a global optimal. But if we add a consensus update as well, then we get convergence to global optimality here. Okay, and again, this is not a new result. This comes from a paper from 2013 with Shomo Carr, one of my former postdocs, and Jose Mura, who I think most people here know. So anyway, let's just show an example here. This is an example of a simple example of a Markov decision problem where we have binary states and binary actions. We build this graph through two nearest neighbor connectivity. So we're going to build the distributed, the bipartite graph that I mentioned in that way. We have 40 agents here, and all fully distributed. And on the left, we're just showing, so there are 4 Q factors here, binary states and actions, so 4 Q factors. On the left, we're comparing the convergence of centralized Q learning and distributed Q learning for just a typical agent. So they all look more or less like this. You can see that basically centralized converges a little more quickly, but distributed also converges as well. And on the right, I just chose 10 of these 40 agents just to show how they achieve consensus. And again, there's 4 Q factors, and they're all just achieving a consensus there, as you can see. Okay, so got out of time, so let me wrap up. So first of all, the main thesis of this talk is that wireless networks can be platforms for machine learning. And then when we looked at 2 things, we looked at federated learning, and there we mainly looked at the interaction between the wireless network and the machine learning algorithm. And then we looked at fully decentralized learning, where we looked to see, we saw that consensus is a way to either consensus in the case of Q learning, or collaboration, other types of collaboration in the case of more general machine learning, are ways to allow us to learn models or actions. Now, I just want to mention some research issues that come up in this area, and then I'll be done. I'd be happy to take questions if we have time. So first of all, in all the problems I talked about, I really basically abstracted the machine learning, okay? So I just assumed that the devices have infinite capacity. Their machine learning was abstracted to this parameter beta in the case of federated learning. But in reality, of course, end user devices are limited. They only have a certain amount of energy, a certain amount of storage. a certain amount of compute power, and they also have to do a lot of other things. This machine learning is not their only task. So that means there's a lot of trade-offs. That is, if you're going to do a neural network, for example, how many layers, how many neurons per layer, what quantization of the coefficients should you use, how much energy should you devote to machine learning? That's a trade, all trades off with accuracy and so forth. So I didn't talk about that. There is work in that area, but this is a very important problem in making these things practical. Also, in everything I talked about, there was a lot of homogeneity, all the data, each device had its own data set of the same size. It was IID from device to device, and all the devices had the same capabilities. They didn't have any different limitations. But in reality, of course, different devices have different capabilities. They have different size data sets. The data sets may be correlated, and the devices may take different amounts of time, for example, to converge their local training. So that means they can't all update at the same time. And there's all kinds of issues there that come into play. This can bias the federated learning in particular. This can bias the updates and so forth. So there's a lot of things to consider that I didn't talk about, and just make you aware of these. And people, of course, are working on these now. These are open research questions. Also, communication efficiency. I just talked about the issue of having enough SI&R. But of course, there's a lot more that you can do. You can do coding, and because the end user devices in federated learning are learning the same model, and they're also collecting data perhaps contiguous to one another. There's a lot of correlation between the data they have and the models they're transmitting. So that means that we should be able to do some kind of distributed source coding to get greater efficiencies of upload. Also, another point is that the data that end user devices have is not big data. It's going to be sparse typically. Training sets are going to be small. So we're not talking about, being able to train very sophisticated models just from data. So that brings up the idea of incorporating domain knowledge in the learning going on at end user devices. So things like deep unfolding and other kinds of methods for doing gray box learning versus black box learning. And then finally, I mentioned privacy, talked about differential privacy, but there's some other things to think about. One is the fact, for example, in an IoT network, the end user devices are typically very simple. They're not smartphones, so they may not be able to implement very sophisticated security primitives. So it may be hard to authenticate all the end user devices. You may have hundreds of IoT devices, and they're not all easily authenticated. So there could be some malicious end user devices, and they could poison the machine learning model or other kinds of attacks. So we need to have algorithms that are robust to that kind of thing. And then finally, I'll just mention that, I talked about federated learning having a server or an aggregator, and fully decentralized learning not having that. And there is something in between, which is serverless federated learning, where you use, say, for example, blockchain to do the aggregation rather than having an aggregator. So, for example, all the end user devices could write their models onto a shared ledger, which they can then all look at, and then they can do their own aggregation, that sort of thing. So that also has a bit of a privacy preservation issue, because there's no aggregator who might be a malicious in their own right, or so-called a curious aggregator. So there's a lot of research issues going on. Here's a few papers that appeared recently in this area. The thing about blockchain I mentioned appears in the IoT journal. Differential privacy, this paper appeared in the Transactions on Information Forensics and Security. Communications efficiency, there's a review paper from last year in the Proceedings of the National Academy of Sciences, and some other papers on scheduling and quantization and so forth. So with that, I'm done. Happy to take questions if we still have time. And I thank you for listening to what I had to say. So thank you.
Thank you once again for the very nice presentation and talk. Now you move to the Q&A section. We have some questions from the audience. So if you have any question, feel free to write it in the chat box or to raise your hand and make the question by yourself. Okay, let me read some questions. One question is about the federated learning numerical results. Does the distribution of the 10,000 samples among the 100 devices has a strong light impact on the obtaining trends?
That's something I mentioned at the end. I think this question came in before I finished up, but absolutely. I think one of the big issues is heterogeneity. So if different devices have different amounts of data, that's going to make a big difference. Also, just as I mentioned, the computational capabilities of devices could be different as well. And that also can make a difference because they may not all finish at the same time. So yeah, that's right. This is an idealization, as I mentioned before. And certainly there are things that are going to affect it. And these are worthy of study, of course, for practical implementation. Thanks for the question.
Okay, second question. In a scenario where it's hard to train a global optimal model for all agents, could federated learning or decentralized learning cluster agents that are correlated and train local optimized models?
Yeah, that's a good question too. And in fact, here I just assume that all the end user devices were trying to train the same model, but there are other studies where, and it's actually a sort of more practical case where subsets of the end user devices are training a local model, but they're not all training a common model, but they're not all training the same common model. So some cluster, you're right, some cluster of end user devices have one model in common, and others have another model that they're trying to train. So, that's a more natural situation, right? I mean, here I've just assumed that the universe of end users are those trying to train one particular model, but certainly in practice, different users are going to have different interests in different models. So yeah, it's a good point. I didn't mention that before. And by the way, there is some work, Technical University of Berlin, on having the aggregator detect those clusters. That is, it may not know in advance which clusters are trying to do which models, but by what they upload and the models they upload, it can start to separate out end user devices into clusters that are trying to learn different models. So there's a way to do that kind of adaptively, even with the aggregator not knowing what's happening. So yes, pretty interesting work.
Okay. I have one question before I move to the other question for the audience. It's about mobility, okay? How to deal with mobility in edge learning. I mean, the connection between the participating devices and the edge service, it seems to be transient due to the mobility of device owners, right?
Yep.
So how to guarantee a low latency learning process?
Great question, Daniel. So, again, I said at the beginning, this is a very, pristine examples we're looking at here, but one of the things that the aggregator could do, and one of the things that could be learning, is the mobility of the in other words, a mobility model could be learned, right? And using that, it could start adapting the scheduling algorithm. So the scheduling algorithm is a decision algorithm, right? So that's something also that machine learning can learn. So, depending on the relative dynamics of the learning and the mobility, the scheduling algorithm could also be learned too, right? So I think you're absolutely right. I think that's a very intriguing question.
Yeah.
How to do learning. So there's two kinds of learning. There are the models being learned by the end user devices, But then the scheduler needs to also learn, I mean, the aggregator also needs to learn the scheduling algorithm. So yeah, that's a great, really nice
it's a
research.
good question. Yeah, thank you. One question from the audience. Could you please give an example of the use case when Asian information aware scheduling for federated learning outperform other scheduling strategies?
Yeah, so that's a good question. I haven't really thought about the use case per se, although you know, I could imagine that in a situation like say autonomous driving, where you're trying to learn some local environmental characteristics, you might want to be sure that every car, which would be what the end users are, has opportunity to upload in some more effective manner. So, you know, if you can converge faster, that means that, you know, if you have, you know, latency issues or what have you, that anything that helps you converge faster is going to be helpful. And one way to do that is to as we saw, at least in that example, is to minimize the age. So, you know, I would say autonomous driving might be a good use case, but factory automation might be another one where there are some time, you know, some fairly rapid time scales. So it's a good question. I mean, I think in general, applications of federated learning and distributed learning are still emerging. And I don't think we have really a good grasp on what exactly the right or killer application is right now. But you know, it's certainly something that once we develop the algorithms, we can start looking at use cases. So,
okay, thank you. I have one other question. It's about cloud learning and edge learning. I think they can complement each other, right? So yes. My question is how to design an efficient cooperation between cloud and edge learning?
Yeah, so I mean, I think this is a more general question of cloud, you know, of edge computing, you know, cloud fog edge computing, right? So, I mean, I think, you know, each of them has a certain quality, if you would say, quality of service characteristics. So all the way at the edge, you know, you can reduce latency. All the way in the cloud, you get more computational power and more data. And then fog is sort of in between. So every computational task is going to have its own parameters, right? You know, some things can take longer, need more data. Some things you got to do quickly. So I think having these hierarchies of computing with different quality of service characteristics allows us to optimize adaptively for a given task where we're going to do the computing. And then machine learning is the same way, right? I mean, if you want to build a model that you're going to keep for a while, you need a lot of data and so forth, you need to push it up into the cloud. If you need something ephemeral that you're going to just use quickly and then move on, like in autonomous driving, you know, there's no need to go to the cloud and collect a lot of data. You want to do it quickly right there near the edge. And there may be other applications in between, right? So where the time scale is not so important and you need a little more data. So I just think this, it's like QoS, right? You know, for some application, like in transmission, you know, it's the same thing. You know, for some applications, you need low latency. For some applications, you need high data rate. For some applications, you need this and that, right? So, you know, it's just a trade-off, and it's another type of trade-off that we have available to us now in networks. And it applies to all computing in wireless networks, but it also applies particularly to machine learning, which is one computing application.
Yeah, yes. Yeah, we have another question. Can we adopt federated learning in the scenario of industry 4.0, where ultra reliable low latency devices operate together and manage interference inside indoor settings of the factory?
Yeah, I think that's a good question. I think that is one of the potential application is when you need, so URLLC, of course, is very high, very low latency, right? And I think one of the situations where you would like to have that is in, and where you'd like to use federated learning or even decentralized learning are in those circumstances where you have requirements for low latency. So I think, yeah, automation, Industry 4.0, factory automation, robot control, those kind of things. I think those are things where, you know, this kind of this pushing machine learning out to the edge is almost essential, right? Because if you try to run a factory and you're, with robots going around, or a warehouse and so forth, and you're pushing the learning up to the cloud somewhere, the latency is going to kill you, right? So I think I think Industry 4.0 is kind of like the poster child for this kind of stuff. So.
Okay, we have some questions in the QA box. The first question is beta the same across platforms, or is it bounded by the worst error among all platforms?
Yeah, so I thank you for that question. In my case, it's a total abstraction, right? That you could think of it as the worst case, as you suggest, but whatever it is, it's the same across all. Now, the analysis would allow you to make it different. You could give a distribution, for example, across, but I don't have that in the slides, but you could do something beyond that. And in fact, in real life, it's going to be different. Different devices are going to have different epsilons. Different betas. Yeah, okay. Epsilon is the overall generic one, but betas, right? Mm-hmm.
Okay, another question is in decentralized learning, the model is shared between agents or also between their data sets?
Just the model is shared between agents, not the data.
Yeah. Okay, let me check if we have more questions. No, it seems I have a final question. Actually, is about the noise. You talked about the noise, and the noise can be used, can be exploited for the learning performance, right? And because conventionally noise in wireless communications is considered as the key impediment for reliable communications. Mm-hmm. So usually in wireless, when I started my master PhD, the main focus was to mitigate noise using channel coding, diversity, and etc. But right. When you go to the learning perspective, the channel noise, it can be benefic to the learning process. So my question is how to regulate the channel noise to be benefic in this learning and driven process.
So I'm not sure I understand your question, but we're talking about the privacy aspect of it, adding the noise.
Yeah, because there is a kind of trade-off, right? We have the privacy and you have the performance, as you mentioned in the presentation. So, but the noise, if exploited properly, we can improve the learning performance, right? So, is there what do you think about, regarding this level of noise, how to regulate to have a good trade-off? Is there an idea factor?
Yeah, I hadn't thought about that actually. In differential privacy, it's usually applied in databases. So you just add noise, artificial noise. But yeah, you're right. In communications, we have real noise, whether we want it or not, right? So maybe we get some level of privacy because of that, is I think what you're getting at. And that's true. And I don't think anyone's really looked at that, as far as I know, that whether the innate noise that we have is enough to guarantee some form of privacy. But that's a good question. Here I'm sort of assuming that the thing that we're encoding to transmit got noise added to it. Artificial noise. And then of course there's channel noise that is going to affect the transmission, but it's not part of that. We get rid of that by decoding. But yeah, you could think about, and by the way, another type of federated learning uses analog, they call it aggregating over the air, I guess. Everybody transmits synchronously in analog, their gradients, in this case gradients, and they add at the receiver over the air. So nobody ever, the aggregator never sees the individual updates. They all add over the air. In that case, the channel noise or any noise that's added physically would be privacy preserving. I hadn't thought about that, but that's an interesting concept.
Okay. Thank you. Maybe I think we don't have more questions from the audience, from the participants. Now we are moving to the end of the seminar. I would like to thank you again, Professor Vincent, for your time, for this very nice presentation. I would like to thank all attendees for joining us in one more Telecom seminar, and hope to see you again in 2 weeks.
Okay, thank you, Daniel. Thank you all for listening. Thank you for your questions. Thank you, Daniel, for the introduction and for the invitation. And I hope everyone has a good evening. So thanks a lot.
Thank you. Thank you so much.